Yeah, definitely. Thanks, Charles. So next up we have DeepForm, and this is a collaboration with a group of folks, some of whom will be speaking: Jonathan Stray, Andrea Lowe, Gray Davidson, Hugh Wimberly, Daniel Fennelly, and myself. And this is a project to extract data from forms. And specifically, we've been working with data on political ad campaigns for television, where the task is to, for a given political ad, extract how much money was paid for that ad, what the organization was that paid for it, the dates that the ad was screened, and so forth. And that's the concrete problem, but you'll hear more about how this fits into a much larger context of extracting structured data from forms in general, whether that's for receipts of this kind or for climate science data, and much, much more. So I'll hand it over.
I'm Jonathan Stray. I'm here with Gray Davidson, and we're gonna walk you through the DeepForm work, which is, we've got a few other speakers here for you today, including Andrea, because it was quite a big project, so there were a bunch of us involved. So what's the challenge? Well, we're taking a crack at a problem that appears in many contexts, not just journalism, but here you can see a tweet. There's a climate scientist who has these historical weather data records, and they come in a lot of different formats because every weather station had their own unique weather log. And on the right is one of 80 million pages in the recently unearthed archive of the Guatemalan National Secret Police. In particular, this archive contains the only records of thousands of people who disappeared during the Guatemalan Civil War. And again, it's every conceivable type of form. I come from the journalism world. I worked as a data journalist for some time. And this is a huge problem in journalism as well. You may have seen this file, or this story, the FinCEN files, which was a huge global collaborative analysis of thousands of leaked special activity reports, or suspicious activity reports. These are the forms that banks file to governments when they think they're something that maybe kind of looks like money laundering. And what I want to direct your attention to is that a huge part of this work was literally transcribing narrative information into Excel files, right? 85 journalists in 30 countries for a year. So yeah, I've done a lot of work on AI for journalism, and my sort of broad conclusion is that while there's enormous potential in terms of pattern recognition, data mining, lead generation, all this stuff, really, if you want to increase the efficiency of journalism, you should use AI for data preparation and cleanup, because that's what takes all the time, and that's where the well-defined opportunities are. So with that in mind, this is a project that we began on in March of this year, and it was simply to unlock ostensibly public data. This stuff is available from the Federal Communications Commission, and what this is about 100,000 PDFs every 2 years, filed by everybody who buys a political ad on TV, on a local television station. So here's what one of these things looks like. You know, it's an invoice basically, and we're interested in a few pieces of information. So for example, the station name, the advertiser name, and the amount that they paid. So not so hard, right? There's lots and lots of tools that can solve this problem. The challenge is that it's not just one form, it's also this form, right? A completely different layout with very similar information. And also this form, which doesn't really look anything at all like the others. In fact, most TV stations use a different format, and so there's hundreds of different formats. There's a very long tail of ways this appears. So that's what we were doing here. We were trying to actually extract this data because it was relevant to the 2020 election. We wanted to be able to provide it to journalists. But more, we wanted to demonstrate that this is a solvable problem for other fields that have it. And as a not insignificant side effect, we wanted to create a data set where people could work on this problem, because it turns out it is actually a state-of-the-art problem. Now I'm going to turn it over to Gray and Andrea, who are going to walk you through what the training data looks like.
Cool. Thanks, Jonathan. So our data consisted of the political advertisements for TV contracts, orders, and invoices from this year, which amounted to approximately 115,000 PDFs. and these were collected using the FCC API. For our training set, we sampled 1,000 of these and hand labeled the fields for contract number, advertiser, flight dates, and gross amount. The full data set and this labeled sample are both available at overviewdocs.com, where you can download that. And we also had additional training sets from previous years. So the first was 17,000 PDFs from 2012. These were labeled through crowdsourcing by ProPublica and made freely available. And then the second was 2014 documents. These were labeled through a semi-automated extraction process that was created by Alex Burns from the Washington Post. And for this process, he used a computer vision algorithm to focus on the page region where the answer is typically found. So after these PDFs were gathered, next slide. We had to process them to use the model by first making sure they were machine readable through OCR, or optical character recognition. Then we tokenized the text and created a document with the corresponding geometry, where the labels were the tokens themselves. The next step here was marking which token out of the document corresponds to the target for the fields we're looking for. So I'm now going to hand it over to Gray so he can discuss that process.
Thanks, Andrea. So at the left, we can see the 6 columns that were the result of that OCR process, the page number normalized, because some of these documents were 5, 8, or dozens of pages long. And then the bounding box for coordinates showing where the token was on the page, and then the token text. So this is the key piece for the next step here, where we then used a fuzzy matching process to decide which tokens matched which targets. So we can see that the red boxes here circle the times when the fuzzy match got a perfect match. And most of these targets that we were looking for, most of the labels were 1 token long. So we can see contract number is the highest one down at the bottom with the flight dates. And in the middle, we can see that the committee, Mike Bloomberg 2020 Incorporated, was 4 tokens long. So we also had a process for finding multi-token targets. The green boxes are surrounding some near misses. We can see that numbers and dates were rated highly for those particular targets, even though they weren't the correct answers. And so the fuzzy match still gets a high percentage, but still finds the correct answers when they're present. So by this process, we were able to determine which tokens corresponded to the targets that we were looking for. And the additional features here, these 6 columns at the right, along with the bounding boxes and page numbers, were the inputs to the model itself. So we can see that we had features such as how much is the token like a digit, or like a string of numbers? How much is it like a number of dollars, etc. And then at the far right was a key column that shows for a given token, a 0 indicates that that token was none of our targets. And then 1, 2, 3, 4, and 5 indicated that it was one of our targets, and the different numbers corresponded to the different targets. So back to you, Jonathan.
So one of the challenges in building a model to do this classification, it's because it's basically token classification, is that the documents have a huge variation in length. Some are, the top half of a page. Some are, dozens of pages of listings of hundreds of spots. And so we had to adapt the length. In the end, we just went with a very simple windowing scheme. The window length is fixed and short, maybe between 20 and 50, and we're just doing multi-class prediction for each token in each window, and then averaging them all of the overlapping windows on top of each other to get the final outputs. And this is what the model actually looks like. So it's actually pretty straightforward as these things go, because the vast majority of the work inevitably turns out to be doing all of the data engineering and OCRing 100,000 documents and so forth. So for each token in the window, we have an embedding from the vocabulary. We pick the 500 top tokens that appear across all of the training data, as well as the token's location on the page and some of these hand-coded features like, does it match a regular expression for a dollar amount? So then we repeat that k times, we go through a few hidden layers, and then we produce a softmax output for each window. So for each class. So rather than just producing one class for the central token in the window, the network tries to predict all of them. And we found that this actually really improves performance by 10% or more. You can think of it as kind of a multitask training approach, where by asking it to label every single token in the window, you force it to learn better intermediate representations in the previous layers. And this is what it looks like. So what you're looking at is the accuracy on the answer in the final document. It's noisy because during training, we just sample from the document, so we don't have to do all of it. And you can see that for many fields, we get to 90%. Some are much lower. In particular, advertiser is not doing so well. It's actually, this looks like it's just like 7% or something. It's actually a lot better. It's an old chart. But it is the most challenging field because it spans multiple tokens. And the main problem we're having is it's not getting all of the advertiser. So it may list, miss the first or last word or put something on the end of it. So that's actually, we went through the literature, and this is actually a major limitation of almost every other technique, is that they're almost all built around classifying tokens into strings of tokens. We did, this will be familiar if you're a weights and biases user, we did some hyperparameter search as well. There's about a dozen configurable parameters, and we found that there was sort of a nice sweet spot where we got good performance on the fields. And then we had a really nice evaluation and logging environment in weights and biases, which Stacy is going to demo live for you briefly.
Great, let's try to see if I can do this. Can you see some bounding boxes? Great, yeah, so this is an example from a report that I made to help get started with the benchmark. And here you can see a bunch of the documents, and maybe you can see these colorful bounding boxes on the different tokens. And let's zoom into one in particular. And I know they're pretty tiny, but on each of these bounding boxes, we actually have a confidence score of how good of a match this is for one of the fields that we're tracking. So the ground truth here is in orange, and then there's some lower scoring candidates. You'll see in purple, for example, that's for the contract ID. These pink ones are the advertiser. It should really be all three of these tokens, etc. And you can also interact with these boxes with the slider that we have in weights and biases. So you can see that as I set the minimum threshold higher, some of these boxes disappear. You can also look at some of these on the bottom. There's a lot of numbers. And if I turn off all the ground truth, you'll see that at the low threshold, it's thinking that a bunch of these numbers might be the total. As I increase the threshold, most of those will disappear and we'll get pretty close to just the final gross amount. And you can set up these kinds of visualizations across many items in your validation data. You can set up custom views, comparing it on certain documents or certain fields. And we hope that that's pretty useful for debugging your models. And should we go back to you, Jonathan, or should I just go to the next slide?
Another couple slides in this section.
Yeah, and I'll talk through this next slide. Right, so we made a benchmark. It's up on weights and biases at this URL. We also have a bit.ly at the end because I know this is a little long to type. And what the benchmark is our baseline model and training code that's really easy to get started with. It's either a Docker container or a Poetry setup. We have a fixed data split. Right now, it's just 1,000 labeled documents from 2020 that you can train on. We have the useful visualization setup, and you can track accuracy across 5 fields: amount, flight, date, to and from, contract ID, and advertiser. And the overall ranking in the leaderboard is just the average of those 5 fields. And next.
So overall, we achieved the goal of showing that deep learning is competitive with hand-built systems. So like Alex Burns' sort of template-based systems, and can indeed extract data from form layouts that it's never seen before. And our baseline, as you saw, is actually not very complicated. We got relatively good performance with a relatively simple network. I think sort of from a technical perspective, the performance boost from predicting across the entire window was really the most striking thing. And actually, as we were doing this work, so I wrote a proof of concept like last June for the applied deep learning course that I took at Weights and Biases. From then until now, actually, a bunch of papers appeared on this very problem. So this is actually a state-of-the-art research problem, and the best methods are developing rapidly. So there's a bunch of stuff that you could try if you want to take a shot at this. First of all, we actually ended up only training on the 2020 data, even though we have far more data from other years. And that's because we just never got around to dealing with missing fields. So different years of training data have different sets of fields that are available. So we don't think that's too hard, but remains to be done and could improve the performance a lot. The advertiser field, as we mentioned, is just much harder than the other fields. And there's actually very little work that talks about how to do multi-token extraction in these ways. But perhaps the most exciting thing that we could do is look at other methods. So this was a paper that came out in the middle of our work. It's one from Google that also talks about extracting data from invoices. It uses exactly the same input format that we do, this like tokens plus geometry. So we felt that, great, we're on the right track if that's what Google was doing. And has this interesting self-attention network where it tries to learn how to relate different tokens. We've also seen graph convolutions used for receipt extraction. So this is from an interesting post about how that was put together. In this case, each token is a node and each edge is a horizontal or vertical relationship. So it's a different way of encoding the geometry. I really couldn't say which way works better, but we've got someone who's trying to test it now. And then the current state of the art, maybe, or at least the most sophisticated model currently, is LayoutLM, which is you have a pre-trained BERT model, which hopefully you're also training on a huge unlabeled data set of forms. And then that creates an embedding, which you then operate over. One of the interesting things about this is it actually includes an embedding of the image. So it looks at both the tokens plus geometry format, as you can see across the left there. It says text embeddings and then position embeddings, plus the actual image itself. So it could extract information from the image, such as the font size or whether it's bold or something. And all of these are just sort of waiting to be dropped into the benchmark we wrote, which has all of the sort of infrastructure and data processing that you need around this, logging methods, all that fun stuff. If you'd like to get started, here is a link for you. And yeah, would love to hear your questions.
All right, thanks DeepForm team for that really interesting talk and for this really excellent benchmark. I could gush for a very long time about how beautiful that that interface you built for looking at the results, Stacy, was, but I won't spend my whole time tooting your horn. The one thing I wanted to get your opinions on is sort of the broader context of this form extraction problem. So one that I think the phrasing you used, Jonathan, was that this information is ostensibly public. And it seems like a lot of this production of information, of forms, it's, in some ways it's akin to the concept of paperwork pollution, which is where you sort of externalize a lot of the effort that needs to be done in order to do useful work, get useful information, et cetera, onto other people through the form of creating paperwork for them to do. So I'm curious, how do you see this DeepForm outside of the obvious political ramifications of being able to uncover dark money? Where else do you see this form extraction being able to have positive, ethical impacts on the world?
Yeah, thanks. So I come from the investigative journalism world, and so it just happens over and over there. So I just showed you that example from the FinCEN files. But it's really a frequently asked question. How do I get the data out of these forms, right? Whether that's downloaded PDFs or got actual physical paper from a Freedom of Information request. And so this is something I've been dealing with for a long time. There are now reasonably good tools if you have 1,000 of the same form. That's a fairly well solved problem by commercial tools, although it's still kind of a pain in the ass, frankly. The frontier is in more complicated problems. So this is heterogeneous forms. And it gets even more complex from there, because we're trying to find the same 5 fields on every single form. There are also problems where different forms have different types of information. So it is, for my money, the place where AI would be most impactful to investigative journalism in terms of cost efficiency of applying AI, right? Because that's really what this game is about. You're not going to enable anything that a human can't do, but you might be able to make it 10 times faster or 10 times cheaper, right? And that can really change the economics of journalism production. And the same thing applies in a whole bunch of other fields, right? You saw the climate examples, the human rights relevant archives. There's a big, another big human rights archive of documents out of Syria, for example. And in medicine, a lot of that, for example, referrals still arrive on faxes. And in the post where I was talking about this work, I talked about how they had, I think it was 37 people full-time who were just typing in referral faxes. And so they started to put some automation on that. So, you know, it is a problem which is sort of on the surface of it, sort of unsexy, but actually is hugely impactful and a state-of-the-art challenge.
Yeah, I think that the fact that it is such a, like, yeah, at that intersection of extremely difficult and non-trivial and state-of-the-art and potentially hugely impactful, it definitely makes this a really, really exciting benchmark. I think I wonder if maybe you mentioned that there's this harder problem of, okay, like what if I need to extract from a couple of forms that have different fields in them? But I think one of the things that the natural language processing community has found is that actually learning to do a harder task with exponentially more data actually makes it easier to then do simpler tasks. So learning how to predict the next characters in a sequence, which is an extremely difficult task for for the English language, then makes it actually easier to solve a problem like answering a question about a simple story about like the Babby tasks from Facebook, these like very simple question and answer things, SAT question type things that seem way easier to us than the language prediction problem. So do you think that if we tried to tackle like a really big version of this problem where you could get that kind of a large data set, do you think that maybe we'd be able to solve these simpler problems better with a single general purpose, form to vec network? Or do you think that it's going to have to be relatively like ad hoc, individual data sets, individual problems, things like that?
So I think there is some hope. The layout LM folks are doing something in the direction of what you're talking about. So that I think it's their paper I'm thinking of. Is they're another piece of research. And the way they define, so we built our network to extract a fixed set of forms, and we have labeled data for that fixed set or fixed set of fields. But there's other work that tries to extract every field. So you just give it a form and it just tries to give you back a bunch of key value pairs and said, well, this was the name of this field and this was what was in it. And it gets arbitrarily complicated if you have, complicated formats in the document, like, tables with split cells and sort of hierarchies of various sort. But you can imagine encoding that as, a JSON object type of thing. And so we're starting to move in that direction. So I do think there's hope. One of the challenges is there aren't that many like large data sets of random forms, interestingly enough. So hopefully our work will add to that pile.
Yeah, actually, so Peter in the chat asked a relatively similar question. Is it realistic to hope for a universal embedding of forms in the next few years, the same way that we have universal embeddings for images, for vectors, or for text? Is it just a matter of better data sets? Are there fundamental challenges you think that prevent something like that from happening?
So I think one of the main things you'd want to do is decode it into the field key value type data. So I think that a universal form embedding has to be sort of equivalent to that, and that seems like it's possible. So yeah, I think a universal embedding is probably possible. I think some of the tricks we do with embeddings may not work in the same way. So, if we do a paragraph embedding, we may be interested in the sort of topical similarity between two paragraphs. I'm not quite sure what a distance function over form data looks like. In particular, there's a sort of ambiguity between, do you want two documents to be close if they're the same type of form? Or do you want two documents to be close if they have data about similar objects, right? So do you want to put like all of the police reports from different precincts together? Or do you want to do the police report of a fire together with the fire department report of the same fire? So there's some complicated questions there about the sort of semantics of that space.
Yeah, that is an excellent point. It seems like most of the time omitting information from a form, the way that you like omit a word from a sentence, omit a patch from an image, and try and learn some reconstruction. Like if you're omitting pieces of the form that are shared across all the forms, then it's not that interesting to fill it in. And if you're omitting the information that is actually filled into the form in the specific fields, often like there's no other information in the form other than the place where I wrote my birth date about what my birthday is. So it does seem like a really difficult challenge building that kind of embedding.
Yeah, it's a challenging knowledge representation problem, right? So in the way that predicting the next word sort of unlocked a whole bunch of progress in NLP, what was it, 5 years ago? It's hard to believe that it's so recent. I don't think we found the like challenge problem that will drive progress in general form extraction.
Well, hopefully I think this deep form benchmark is an important step in that direction of building, raising awareness about this problem, of building public benchmarks on which people can work, and sort of driving more research in that direction. So thanks for doing this work and for putting this together.
Yeah, well, thanks to my team. A lot of folks worked on this.